Welcome again, AP Chem students. I hope you can hear me this time. My name is Lou Akampora, the Science Director for Advanced Kentucky, and I know you're getting ready to take the AP Chemistry exam in a little bit more than a week. So we're trying this first inaugural broadcast of Advanced Kentucky AP Chem TV to try to go over a few items that might help you on the exam. Feel free to tweet in any questions you might have. Certainly if there's a multiple choice question from the mock exam that you don't understand why your answer was incorrect, or a free response question, I'm happy to take those questions. But I really want to focus today on something that many students had difficulty with, but really shouldn't. And that is the idea of writing net ionic equations. So, why is this important? Well, I'm sure you've had enough chemistry to know that chemical change is really the heart of chemistry. We start out with reactants, and through the magic of, or the science of chemistry, they become products. And part of the challenge of an AP chemistry student is to be able to represent that process with a chemical equation. And I know you've written chemical equations and know that they need to be balanced to reflect the fact that all the atoms and electrons on the reactant side have got to show up in the product side, and everything on the product side must have come from somewhere on the reactant side. But there's more than that, and the equations really give you a window into what's happening on an atomic level. The big ideas of AP chemistry include, one of the learning objectives is that students can translate among macroscopic observations of change, a precipitate forming, heat being evolved, perhaps a gas being produced, and chemical equations and particle views. And you should be able to make the connection between those. The essential knowledge is that a chemical change may be represented by a molecular equation, an ionic equation, or a net ionic equation. And I'm not sure that all students really understand the distinction and why this is important. Another learning objective in this section is that a student can translate and observe chemical change into a balanced chemical equation and justify the choice of equation type, molecular, ionic, or net ionic, in terms of utility for a given circumstances. So let me go to the PowerPoint here for just a moment and show you some information. And these are our hashtags. So if you are on Twitter, please feel free to Twitter in a question to ask Lou KY. And so what are net ionic equations? And net ionic equations are relevant for reactions that occur in solution, in aqueous solution for us. And that includes precipitation reactions where you mix two solutions and an insoluble precipitate forms, acid-base reactions, and electrochemistry, which commonly, and in terms of AP chemistry, always occur in water solution. Not particularly relevant for a combustion reaction or a gas phase reaction, but these are still fairly important. When you're writing net ionic equations, the equation should reflect only the changes in the reacting species. So if there are other particles there, chloride ions or sodium ions that don't change, they're not included in the net ionic equation, and we call those spectator ions. That's kind of the second bullet there. Phase notation is not required. So even though a reaction might occur in aqueous solution and produce a precipitate or a gas, you're not expected, unless the question specifically instructs you to include phase notation, you will not be required to include it. But the species phases should be indicated by context. So if we have a copper ion, and you do have to show the charge on all ionic species, that would be assumed to be an aqueous solution, whereas just copper as an atom would assume to be a solid. And then the last point here is that many reactions have several species present in an equilibrium of a weak acid. You'll have some weak acid and its conjugate base, but in terms of writing the net ionic equation, you really are only expected to represent the most prevalent species. So let's take a look at a few, oh, sorry. Let's take a look at some practice problems or some sample problems. And the first one, and if you can go back to the PowerPoint, I'm sorry, and go to the next slide. And your teacher may have shared this with you, but here is an example of a situation, an experiment where a net ionic equation would be normally asked for. Calcium chloride is often added as an electrolyte to bottled water. You could read the label on the bottle and see that. In an assay or an experiment to determine the concentration of calcium ion in a sample of bottled water, excess 0.1 molar potassium oxalate, and you are expected to know many of the polyatomic ions. Oxalate is probably not one that you are expected to know, but you're given the formula for potassium oxalate. And you're told the solution is added to 100 milliliters of the bottled water, forming a precipitate. Normally, the first thing you would be asked in this question would be to write the net ionic equation for the precipitation reaction. So how would we do that? And the important thing to note is that even though calcium, and I'm going to work through this step by step. Since we have calcium chloride in solution, many students would just write that as CaCl2, but which would be perfectly good if this were a molecular equation you were asking for or a solid calcium chloride. But when calcium chloride dissolves into water to form a solution, those ions dissociate into one calcium ion with a charge of +2 and two chloride ions, each with a charge of -1. And this really is the reactant. Again, aqueous, the phase is presumed from the context. So our first reactant would be a solution of calcium chloride, and I will represent that as Ca2 plus 2Cl minus. To this, we're adding excess potassium oxalate, and you might recall from the problem that potassium oxalate was had the formula K2C2O4, and even if you don't know what the oxalate ion might be, you could, from the context of the question, surmise that it is whatever is not potassium here. So it would be C2O4. And the charge on this, well, you know, potassium ions have a charge of +1, so the oxalate ion must have a charge of -2. And I will go ahead and write all of these species. Those are potential reactants. They will form a precipitate. And in a precipitation reaction, one positive ion and one negative ion will combine to form an insoluble precipitate. So we have two new combinations. We have calcium ions and oxalate ions, or potassium ions and chloride ions. You don't need to memorize all the solubility rules, but one of the ones that you should understand is that any compound containing a group 1 cation, that's lithium, sodium, potassium, rubidium, or cesium, is going to be soluble in water. And all nitrates are soluble is your second one that you need to know, but that's not particularly relevant here. So we can immediately eliminate potassium chloride as a candidate for the precipitate, leaving calcium oxalate, and the formula there would just be CaC2O4, since calcium ions have a charge of +2, and the oxalate ions have a charge of -2. And the net ionic equation is just what we have on the board here. And that's all you should be writing. Most students who get this incorrect really write too much by either including spectator ions or having the incorrect charges on the ions. But it's not how much you write, it's how well you reflect the change. One question that you might remember from the mock exam this year is students were asked, why is this the most appropriate form? Why shouldn't I include a full equation? And if I were to write the full equation for the same reaction, add that up here, I would write the molecular formula for calcium oxalate, potassium chloride. Oops, I'm sorry, those are the products. Let's try that again. For calcium chloride and potassium oxalate, forming calcium oxalate and potassium chloride, and I balance that here with that too. This does reflect, this overall molecular equation does reflect the changes, but it includes spectator ions, and these spectator ions are not particularly relevant to a gravimetric analysis reaction experiment where you're determining the mass of that precipitate. So net ionic equations don't have to be complicated. In fact, students who don't get credit for these are usually writing more than they should. When you've done a few of these for practice, and we'll see one more in a little bit, but the general schema for precipitation reactions is that the dissociated ions come together to form the insoluble precipitate. So if you were to mix solutions of, let's say, lead nitrate and sodium chloride, well, knowing that sodium nitrate is soluble, the only precipitate possible would be PbCl2. And since PbCl2 is an ionic compound composed of lead 2 ions and chloride -1 ions, the net ionic equation for that reaction would just represent the lead ion combining with 2 chloride ions to form the insoluble precipitate. Should be pretty easy, takes a little bit of practice though. So tweet in any questions or ask your teacher. Precipitation reactions are important. So are acid-base reactions, and these can involve strong acids, strong bases, weak acids, weak bases, and even buffer solutions, which are quite nettlesome. I know many students really have a hard time with buffers, and it's not the math calculations for buffers, but rather understanding the underlying chemistry, and this is where writing the net ionic equation can really help set you up for success on the entire problem. So let's look at one more problem from that sample problem, and this might be an acid-base problem. So we'll go to the next slide, and here's an acid-base titration where 0.10 molar hydrochloric acid is being added to a solution of ammonia, and most of you probably know that ammonia is a weak base. If you had forgotten that, the fact that you're given a base dissociation constant for ammonia would be a good hint. And then you're asked to two parts here to first write the net ionic equation for the reaction that occurs during the titration. And then the second part would be to say at the equivalence point of the titration, is the pH less than 7, equal to 7, or greater than 7, and to justify your response. So let's take a look at how you might answer that. If you've done one of these titrations, and I'll just kind of sketch this out because I'm a visual learner. I've got a analyte of ammonia, and I've got some 0.1 molar hydrochloric acid as my titrant. And don't worry about the words like titrant and analyte. They're kind of fancy, but you get the idea. And we're going to drip this in, and a reaction is going to occur. Again, understanding what the reacting species are, because hydrochloric acid is a strong acid, we don't write it as HCl, but rather H plus Cl minus. In aqueous solution, strong acids ionize completely to form hydrogen ion and some other ion. And we're adding this to a solution of ammonia, whose formula is NH3. Any strong acid, this reacting species is hydrogen ion. Ammonia is a weak base and is therefore a proton acceptor, and therefore the product would be NH4 plus the ammonium ion. And again, students are often confused by ammonia, ammonium. They're different particles. Make sure you get the formulas and the charges correct. And what happens to the chloride? Well, nothing. Chloride's a spectator ion. So we can just get rid of it. If you're writing it on your AP paper, it's perfectly okay to just cross it out neatly. And this would just be the net ionic equation for that reaction. If we were carrying out this experiment, this titration, we might be monitoring the pH. You might have a pH probe in here. And what you would see, here's my pH versus the volume of 0.1 molar hydrochloric acid added. And since we're starting with a solution that's a weak base, the pH would be up here somewhere greater than 7. And we would expect to see the pH drop slowly as this reaction takes place. Because as we're adding hydrogen ion, the amount of ammonia present will decrease as ammonia is consumed, and the amount of ammonium ion will increase as it's produced. And then we'll see a fairly sharp drop off. And right about here, where the drop is the steepest, where we've added the same equimolar quantities of hydrogen ion and ammonia, is what we call the equivalence point. A very common question is to understand what is true in this solution at the equivalence point. Is the pH 7, which is, of course, neutral? Is it above 7 or is it below 7? And why? And many of you, if you've done a titration with a strong acid and a strong base, the equivalence point occurs right at pH 7. In this particular case, we've got a strong acid reacting with a weak base. So when I've added equal amounts of those, just kind of the way we use language would make you think that the acid is going to be a little bit more powerful and take the pH below 7. And that is actually not a bad way to explain it. The equivalence point pH will be less than 7. Another slightly different and maybe a little bit better way of explaining it is to say that at the equivalence point, we've converted all of our reactants to a ammonium ion, which is itself a weak base, being the conjugate, or which is itself a weak acid, being the conjugate acid of the weak base ammonia. And because we now have a solution of a conjugate acid, the pH will be slightly acidic. So again, not much writing here. And students who miss this question really tend to overwrite and include more than they really need to. What do you have to know? Well, you've got to be able to identify ammonia and hydrogen ion as a reacting species and understand that they come together to form the ammonium ion. So there's an acid-base practice question. We've got a couple more here. So let's go ahead to the next one. And here's another gravimetric analysis. Some of you may have actually done this lab. You are responsible for knowing what alloys are in the AP chemistry curriculum. And alloys are just mixtures of metals, things like brass or bronze or steel. Are not elements of the periodic table, but mixtures of elements that have different properties. They're not compounds. There's no stoichiometric ratio among the elements, but they are mixtures of solid mixtures. So sterling silver is generally an alloy of the elements silver and copper. And if you were doing an experiment to determine what percent silver and what percent copper, you might take a sample of the alloy and completely react with 6 molar nitric acid, a very strong oxidizing agent, forming a solution that contains both silver 1 ions and copper 2 ions. You would then precipitate the silver ions by addition of excess 1 molar sodium chloride. And an important chemical fact to know here is that silver chloride is insoluble and will precipitate, but copper chloride is not insoluble. Soluble and will remain in solution. You can then filter off the white precipitate, wash it, dry it, and determine how much silver chloride you have. and knowing that, figure out how many moles of silver were in your initial sample. But in terms of this equation, this part of the problem, we want to write the net ionic equation for the precipitation reaction. So let's see what we would do here. Again, the reactants are silver 1 ions. And let's go back to the board, to the whiteboard.
Right.
So the reactants here are silver 1 ions, even though you're not told, and you may not even know what the counter ion is. When we oxidize silver ion with nitric acid, we get silver nitrate, but the silver 1 ion is the species that will form the precipitate. We are reacting with excess sodium chloride solution, and since it's a solution, I will write these as dissociated. And most of you, I think, now can say, well, I know that silver chloride is insoluble, so we will just form the precipitate of silver chloride. And what happens to the sodium ion? You got it. It is a spectator ion, so we either cross it out or don't even write it. Not how much you write, just how accurate you might be. As long as we're on this problem, let's go and throw in a little bonus question, which might be, okay, Mr. A, you said, this is what happens at the end of the reaction. How did we go from that silver metal to the silver ion? We oxidize it with nitric acid, and that's an oxidation reduction reaction. We know the reactants are silver metal. I'm going to write a little 0 up here just because it's my thing, but this tells me it's uncharged, it is silver metal. You could write a little solid in parentheses down there, and that would mean the same thing, but I think the 0 looks a little bit neater. Nitric acid would be my other reactant, and even though we might be tempted to write HNO3, it's a strong acid, so we're going to separate it into its reacting ions, H plus and NO3 minus. And remember, the charges are important. And if you write H and just NO3, you are going to be wrong. We know one of the products is silver ion with a +1 charge. And then there are a couple of other products that you may or may not know. This is as far as you need it to get for the question we just looked at, but I'm going to go ahead and look at this. It's clear that silver atoms become silver ions by losing 1 electron. So somewhere in here, something's got to be gaining electrons, and our candidates are hydrogen ion and nitrate ion. It's unlikely to be hydrogen ion. In this case, silver is a very unreactive metal and does not react with any strong acid. And it's the nitrate that is, in fact, the oxidizing agent. You're probably not expected to know this, but when nitrate is oxidized in acidic solution, one of the products is, or its product is nitrogen monoxide. And that really is our skeletal equation. Let's go ahead and, because we're here, balance this and come up with a net ionic equation. So we already have oxidation numbers for silver metal, which would be 0, and silver ion, which is +1, and that's reflective of the fact that silver atoms lose 1 electron each to become silver ions. The other species changing its oxidation number is the nitrogen atom, which is part of the nitrate ion on the reactant side, but part of the nitrogen monoxide molecule on the product side. If you add up your oxidation numbers, and you can do this at home, but the oxidation number for nitrogen here is going to be +5, because +5 and 3 -2s gives me -1. The oxidation number of nitrogen on the product side is +2. And in a very formal sense, the nitrogen atom is gaining 3 electrons, and that really is the skeletal outline for balancing this equation. Since the same number of electrons has to be gained and lost, unless you know something we don't, we better multiply this through by 3 to make sure that we are losing 3 electrons. And that means I need 3 silver atoms and 3 silver ions. And now the electrons are balanced. because these occur in an acidic aqueous solution, we then typically have oxygen atoms and hydrogen atoms that need to be balanced. We will balance the oxygen atoms not by adding O2, but by adding water. You've got to have that oxygen in the -2 oxidation state. And I have 3 oxygen atoms represented on the left-hand side. I only have 1 on the right-hand side, so I'm going to go ahead and add 2 water molecules, and that will balance out the number of oxygen atoms. And now for hydrogens, I have 1 here on the left, but 2 times 2 would be 4 on the right, so I need to add a coefficient of 4 there. And that would be my balanced net ionic equation. Notice I don't need to have the same coefficient for my parts of the nitric acid molecule. I can check that this is correct by making sure the total charge balances on both sides. And I've got 3 times 0 is 0, 4 times +1 is +4, and 1 times -1 is -1. So my total charge on the left-hand side is +4 minus 1 is +3. On the product side, we have 3 times +1 is +3, and then 0 and 0. So we have the same charge on both sides of that equation, and that gives a good hint that we've done something right. If you want to practice this at home, try a reaction of copper metal with nitric acid, and you'll recognize when you get it right. Okay, so that was a little bit of redox, a little bit of precipitation in that same reaction. Let's look at what might happen to a buffer solution. Probably another important instance of net ionic equations. So if we go back to the PowerPoint and look at question number 4, and your teachers should have these questions if you want to practice them in class or review them. So our next slide would say that we've got a small aliquot of 1 molar sodium hydroxide solution is added to a buffer containing equimolar concentrations of acetic acid, and that's a fairly common acid, but if you don't know the formula, it's given to you. You're not expected to know all that, along with the acid dissociation constant, resulting in a negligible change in the pH of the solution. So let's take a look and see what's going on. I'm going to answer question B first and then go back to question A. We want to write the net ionic equation for the reaction that occurs when this small amount of sodium hydroxide solution is added to a buffer containing acetic acid and the acetate ion. So let's take a look at the board again. And we have, again, I'll kind of sketch out our buffer here. And our buffer contains acetic acid and acetate ion. And most of you will recognize the relationship between these. This is a weak acid and its conjugate base. So typically they would exist in equilibrium with each other and they will not react with each other. I will write the equilibrium equation here. With Ka value of 1.8 times 10 to the negative 5th. And the expression for the equilibrium constant is just what you would expect, the products over the reactant. So the concentration of H plus times the concentration of CH3, COO minus, that's the acetate ion, over the concentration of CH3, COOH. And we have equimolar, unspecified, but equimolar concentrations of both acetic acid and acetate ion. Well, I guess I'm going to change my mind. It's my prerogative. And I will go ahead and answer question A first, which said, what is the pH of the solution? Because we've almost got it answered. If we know that the concentration of acetic acid is equal to the concentration of acetate ion, then these two terms, these two factors will cancel. And that tells me that the concentration of hydrogen ion will just be equal numerically to the value of Ka, and therefore the pH of the solution will be the negative log base 10 of that. And if I look at my exponent here, I'm going to get a number pretty close to 5, or negative 5 to the log base 10, and the negative of negative 5 will give me a pH of roughly 5. So this buffer would have a pH of 5. What happens now if we add a small amount of sodium hydroxide? And the sodium ion, most of you, I think, guessed by now that is a spectator ion, so it's a hydroxide part that I'm really working with. And this is a strong base, and strong bases do what strong bases do, and they react with acids if there's an acid present. And we've got the weak acid, acetic acid right here. So our reactants for this equation would be CH3COOH plus OH minus. And our products would be, well, this is an acid, it's going to lose a proton. This is a base, it's going to gain a proton. So we will get CH3COO minus plus H2O. And there is the net ionic equation. Why is this a buffer? Someone I hope is asking out there. And it's a buffer because as we add this hydroxide ion, it's going to react essentially to completion. This is a strong acid, and it's going to use up some of this. The concentration of acetic acid in this solution will decrease. The concentration of acetate ion will increase as it's formed. But a small change in these two concentrations will, using this equation, not cause a large change in the pH of the solution. It will really only change the value of this ratio. If we were to add a small amount of hydroxide ion to distilled water, the pH would jump from 7 to 13 or 14. So students who have difficulty with buffers, usually it's not the math that's the challenge, but understanding the underlying chemistry. And if you have any questions about that, I encourage you to tweet in today or any time this week, and I will try to get back to you. Okay, I've got 2 more questions I'd like to look at, both of which involve net ionic equations. One is a galvanic cell, and the other is an electrolytic cell. So let me clear the board while you read this question. It's a little bit more complicated, and there's a few parts to it. So we've got 1/2 cell of an electrochemical cell is constructed by immersing a metallic silver electrode in a solution of 1 molar silver nitrate. And a second half cell is constructed by immersing a metallic zinc electrode in a solution of 1 molar zinc sulfate. These half cells are connected by a conducting wire connected to the electrodes and a salt bridge connecting the solutions. And as it almost always starts out here, write the net ionic equation for the reaction that occurs as a cell operates. That's kind of our theme today. You're asked to determine the cell potential and to understand what happens during the operation of the cell. And we'll see that you're told if the mass of the silver electrode changes by 1 gram, is this an increase or a decrease, and to justify your response. And then does a change of the mass in the zinc electrode, is that less than 1 gram, equal to 1 gram, or greater than 1 gram, and to justify your response. So let me switch back to the whiteboard here, and I will try to draw a little picture here, a schematic of this electrochemical cell. We've got a solution of silver ion with a nice silver electrode in there. And that's 1/2 cell. And then over here, next to it, we've got a second solution that contains zinc ion. And these are both 1 molar solutions. And you should know the charges on the ion, they were given to you, with a solid electrode of zinc metal. And we are going to now connect these 2 electrodes with a wire, and I'm going to put a voltmeter in there because we're going to need it later. And the solutions are connected with a salt bridge. And the salt bridge is typically just a aqueous solution of an ionic compound that is unreactive. It will not react with silver ion or zinc ion or nitrate ion or sulfate ion, but it's going to turn out that the nitrate ion and the sulfate ions here are all spectator ions and will not play a role in the net ionic equation. So I'll just put in K plus here and NO3 minus, since potassium nitrate tends to be unreactive. In order to determine the net ionic equation, we need to know the reduction potentials for these species, and they were on the problem. You certainly do not need to memorize these, and I'll just put them over here since I happen to remember them. Silver ions gain 1 electron to form silver atoms with a standard reduction potential of plus 0.80 volts. And zinc ions gain 2 electrons to form zinc atoms, and the standard reduction potential there is negative 0.76 volts. And I usually like to just put in our standard here, and that's hydrogen ions gaining electrons to form hydrogen molecules, and that's 0.00 volts, because that's what the good people at the International Union of Pure and Applied Chemists have decided. So we decide which of these species has a stronger attraction for electrons, and it's clearly the silver. The reduction potential is a measure of how strongly this species on the left attracts electrons. So we're going to have our reduction occur over here, Ag plus 1 electron going to Ag naught, and over here you can't have 2 reductions occurring at the same time, so we're going to have to flip this around and make it an oxidation to get zinc atoms will become zinc ions by losing 2 electrons. And now we've got the reduction half reaction and the oxidation half reaction. We've got to combine them into our net ionic equation. Since we've got 1 electron being gained over here, 2 electrons being lost over here, we're going to multiply this whole thing by 2, and we're going to get the net ionic equation, which would be 2 silver ions plus 2 electrons. I'm going to go ahead and write those. Those are my reactants from over here, plus 1 zinc atom, becoming 2 silver atoms plus 1 zinc ion plus 2 electrons. And of course, I better have the same number of electrons on both sides. So I'll just go ahead and erase them. Not really spectator ions, but electrons. And this is my net ionic equation. Same thing would happen if you were to drop a piece of metallic zinc into a solution that contains silver nitrate, but in this case we've separated out the reduction from the oxidation. And other typical questions you might see on this would be to ask in what directions electrons flow through the wire. Since electrons are produced here and taken in here, the electrons will flow in this direction through the wire, right to left. What happens in this salt bridge is, now many students think electrons flow through the salt bridge, and they don't. They flow through the wire. It's these ions that flow through the salt bridge to maintain electrical neutrality. Since we've got negative charge flowing right to left, the only way we can not have negative charge build up over here is for positive ions, in this case potassium ions, to move right to left, and negative ions to travel left to right. And we're going to neglect any migration of ions into the salt bridge on both sides. We try to, the salt bridge is there to keep these 2 half cells separate. So we didn't ask this question today, but this is a typical question in the understanding of electrochemical cells. We might want to say, what is the voltage? What would I measure here? And the voltage is just going to be the difference between these 2 values. Some books will tell you to reverse this equation, change the sign of that, and add it. Other books will just tell you to take the difference between those. Clearly, mathematically, it's the same thing. And you would get the standard cell potential would be 0.80 volts minus negative 0.76 volts, and that is 1.56 volts. Notice that you do not multiply this voltage by 2, this potential by 2. Remember, a volt is equivalent to a joule per coulomb, and when you multiply this through by 2, yes, you'll get twice as many joules, but you'll be using twice as many coulombs, so the potential the energy per coulomb will stay the same. Knowing this, we can easily answer the last part C. Does the mass of the silver electrode increase or decrease? And since silver metal is a product of this reaction, it's got to be formed. So the mass of the silver electrode will, in fact, increase. And if the silver increases by 1 gram, does that mean the zinc electrode will decrease by 1 gram? Well, certainly the mass of the zinc electrode will decrease, and certainly total mass is conserved, but the mass of the electrodes is not the total mass, and certainly a lot of the mass of the cell will be taken up by the ions in solution. So if we gain 1 gram of silver, well, we'd lose zinc metal, but only half as many moles, and the atomic mass for zinc is much, much less than the atomic mass of silver. So the loss of mass of the zinc electrode would be much less than 1 gram. And I think that pretty much covers that. So I got one more question to look at, and then still invite you to send in tweets or email me if you have any questions on net ionic equations. But we've got one more cell, and this is again electrochemistry. This is an electrolytic cell, and we're going to pass a direct current through inert platinum electrodes. You probably didn't use platinum electrodes if you did this in your school. Carbon electrodes work well, but the platinum electrodes are kind of a textbook standard. As long as we don't actually have to buy them, we may as well use platinum. And we find that the solution around one electrode turns brown and bubbles of a colorless gas form at the other electrode. So while we're switching back to the board here, let me kind of sketch that out. And we have a solution of potassium iodide. So that's going to contain potassium ions and iodide ions. And we've got 2 nice platinum electrodes here. Those are my platinum electrodes. And I've got a current source, a power supply that is going to pump electrons. And the electrons will be pumped this way and this way. So the first thing I want to know is what is going to be responsible for that brown gas. And we're going to have a reduction occurring over here where something is going to gain electrons. So we're going to gain electrons, and that is chemically called a reduction. Kind of a weird use of language to reduce something by adding things, but that's what we have. And over here, we're going to lose electrons, and we call that an oxidation. And let me look at the oxidation first. When you have a solution, the thing that is going to be oxidized is the thing that is most easily oxidized. So we're going to take an electron from something, and we're not going to take an electron from a potassium atom. Most of you, or a potassium ion, most of you understand that potassium atoms have that one valence electron in the 4s shell, and when they dissolve into water or they form compounds, they form potassium ions. Those are those remaining electrons are held pretty strongly. Iodide ions, on the other hand, will in fact lose electrons. And you might have seen on the problem, you were given the table of reduction half reactions, and always remember to use the information that's given to you. So I'm going to go ahead and reproduce that over here. We had at the bottom K plus E minus goes to K with a standard reduction potential of negative 2.92 volts. We have H2O plus 2 electrons going to H2 plus 2 OH minus, and our reduction potential there is negative 0.83 volts. We have 2H plus 2 electrons goes to H2, and that's one that's an easy one. It's 0.00 volts. We have I2, iodine, plus 2 electrons going to 2 I minus, and there we're at plus 0.54 volts. And at the top here, we've got O2 plus 4H plus plus 4 electrons going to 2 H2O at a plus 1.23 volts. And now we want to know what is going to lose electrons. Well, these on the left-hand side of these arrows are species that gain electrons, with the strongest gainers up top and the weakest attraction down the bottom. And everything on the right of the arrow could lose electrons, with the things that lose electrons most easily at the bottom, and things that that lose electrons with difficulty at the top. So if we just start at the bottom here and come up the list and say, what do we have in this solution that could lose electrons? Well, we don't have potassium atoms. We've got potassium ions, so we can't use that. We don't have any hydrogen molecules. We don't have any gaseous hydrogen there. And we do have plenty of iodide. So what's going to happen at the oxidation electrode, the anode, is the reverse of this reduction. So we will see over here that 2I minus will become I2 plus 2 electrons. And it's this iodine that is brown, is responsible for the brown color. The colorless gas that's formed, well, if we're losing electrons over here, we better be gaining electrons over here. So we'll just start, and the things that are present that most easily gain electrons will be on the left, and we'll start from the top down. We don't have oxygen present. We don't have iodine present in the solution. We don't have a strong acid, but we do have plenty of water. So even though it might be tempting to try to add electrons to the potassium ions, in this case, the water itself, I might write that there's plenty of water in here. In fact, the solution is mostly water. It is the reactant. So all we need to do is copy the reduction of water, and we would see that H2O is, I better put 2 there to balance that, is going to gain 2 electrons to form hydrogen gas and hydroxide ions. And we would see little bubbles of hydrogen gas coming up from those electrons. Once we've identified those 2 half reactions, the net ionic equation just combines them, and I've done all the hard work already, and this is easy because we've got 2 electrons being lost and 2 electrons being gained. So the net ionic equation just combines these reactions. I don't have to multiply through by any coefficients. So I'm going to have 2I minus plus 2H2O goes to I2 plus H2 plus 2OH minus. And we're finished with this. So I'm going to make this board a little bit less busy for us. Part of the challenge here is recognizing that water is in fact a reactant, and it's not just a solvent, and it's a reacting species in this net ionic equation. But you'll always be given the table of standard reduction potentials, and be aware of both the oxidation and the reduction half reactions of waters, because reactions that occur outside of that window probably are not going to occur in aqueous solution. So here's my net ionic equation. A good question might be, what is the minimum voltage I need on this power supply, my external voltage? And I've just erased what the information I need here, but if you were to calculate the potential for this reaction, the E naught for this reaction in exactly the way we did before, you would find I would get negative 0.83, and that was the standard reduction potential for this volts minus what I had here, which is the 0.54 volts, and that is negative 1.37. I think I did that correctly. Yep, volts. So my cell potential is negative 1.37 volts. In order for this reaction to actually occur, the external potential plus the cell potential must be greater than 0. And That means my external power supply must be greater than positive 1.37 volts. So you would have to have a power supply here that was powerful enough to push the electrons through and get this to happen. And then often you'll see these questions coupled in with a little bit of thermodynamics. One of the important questions to ask is, will this reaction occur spontaneously? And that translates into the plus minus sign of the delta G, the change in free energy for the reaction. Generally, for any electrolytic cell, if we have an external power supply, we are putting energy into it. This reaction will not occur by itself or spontaneously or thermodynamically favorable, and therefore the delta G for this reaction is going to be positive. Most of you should know the connection between the plus minus sign of the change in Gibbs free energy and the spontaneity of that reaction. So I've gone over 6 problems here. I hope that's helpful for you. The crux of this is writing net ionic equations and being able to describe chemical changes that occur in experiments. And it's a skill that students struggle with because you are really invested in writing full molecular equations, and often students don't get credit because you write too much. So there are some things to practice on and think about. Again, if you have any questions for me, please feel free to send them in, and I will try to respond to you. But good luck in this coming week. I know you can really review a lot of the good chemistry that you've learned and feel good about the AP chemistry course. So good night and thank you.